Hi, everyone. Thank you so much for inviting me to speak at this conference. I'm very sorry I could not be there in person, but I'm very happy to share some of our work that we've been doing in Phong Nha-Ke National Park. My name is Kathleen Johnson. I'm an associate professor in the Department of Earth System Science at the University of California, Irvine. And I've been working on Southeast Asian paleoclimate history, or the history of past climate change, since around 2010. And prior to that, I've done a lot of work on past climate change in China for the East Asian monsoon system. The work that I'm going to show is the result of several efforts from my PhD student, Elizabeth Patterson, and my close collaborator, Michael or Mick Griffiths, as well as many other collaborators, both in the US and Vietnam and elsewhere. So today I'm going to talk about how we can use paleoclimate information or geochemical information from stalagmites or speleothems to study past climate change. Once again, I just want to reiterate that it's been such an amazing opportunity and pleasure to work with the researchers and management of the Phong Nha-Ke National Park. Here's a photo of some of our research team from our most recent visit in March 2023 near the trailhead that accesses one of our other cave sites that we've been studying. To say a little bit about the motivation for this work, climate model projections of tropical and monsoon rainfall are still highly uncertain. So shown here are projections of future rainfall change for 3 different scenarios with 1.5 degrees of global warming versus 4 degrees of global warming, and then an intermediate number. We know that in general, precipitation is projected to increase over high latitudes and parts of the monsoon regions, but some areas in the subtropics are actually projected to decrease. So if you'll look at these maps, the tan colors show you areas which are projected to become dry. And you can see that mainland Southeast Asia actually shows up as becoming drier in the future. But in addition to becoming drier, we do know that there will also likely be an increase in the frequency and magnitude of extreme rainfall events, such as during typhoons and other tropical storms. And so one of our concerns, though, is that there's actually a wide range in climate model projections for rainfall in this region, with some even showing that it will get wetter. And so understanding which models to trust relies on, in part, our understanding of how well they're simulating the physics of the climate system and understanding the mechanisms that drive rainfall change in Southeast Asia. And one way that we can test these models is through using paleoclimate data. So paleoclimate is the study of past climate change, and it's incredibly important subfield within climate science that helps us clearly identify the human-caused component of observed climate change, as opposed to what might be caused by natural forcings or natural internal climate variability. So it provides blueprints for the combined effects of both these external forcings, for example, the response of climate to greenhouse gas changes, as well as to internal feedbacks in the Earth system, for example, the response to things like the El Nino Southern Oscillation. It also helps us set boundaries and provide alternate conditions for climate models in order to test how well they can simulate a climate very different from today. And so overall, the motivation for this work is to add confidence to projections of future climate change in the region. And so the tool of choice that we use in my research group are speleothems. Speleothems are these calcite formations which form in caves, which we all know Phong Nha-Ke has many caves. And they form as a result of water dripping in the cave. So rain falls on the surface. That water can react with carbon dioxide in the soil, becoming slightly acidic. And then as that water moves down into the cave, it dissolves the limestone bedrock and then enters the cave where it drips, degasses, and precipitates calcium carbonate in these nice layered formations. So these layered formations, like stalagmites, can be extremely useful for studying past climate change, in part because we can actually use a method called the uranium thorium method to date them very precisely. We can also measure different chemical markers along their whole growth axis, things like the isotopes of oxygen and carbon, the trace element composition, and many other things. And all of these measurements can tell us about past rainfall at this location. And then we can compare that with other data and with climate models to understand the range and mechanisms of natural rainfall variability. But in order to do this, we also need to study the cave systems themselves. And so this is the reason why we come to do fieldwork a lot at Phong Nha-Ke caves, and why we are monitoring the environment in some of the caves that we're working on continuously. So we want to understand how changes in the cave environment, like temperature, humidity, drip rate, drip water chemistry, and the PCO2 of cave air can impact the signals that we're recording. Another motivation for this work, in particularly looking at Phong Nha-Ke caves, is the fact that the climate of Southeast Asia actually mostly is dominated by summer rainfall, as you all probably know. So during the summer, we have winds that are bringing moisture from the Bay of Bengal and the Indian Ocean, from the southwest to mainland Southeast Asia, with most of the rainfall, for example, in Luang Prabang occurring, and Nakhon Phanom occurring during the summer months of June, July, and August. And we are actually working on a couple of cave sites here, one in northern Laos and one in central Laos, which I'll mention a bit more later, both of which are dominantly affected by the summer monsoon. We are particularly interested in central Vietnam, though, because this location is quite unique if you look at the rainfall patterns here. Dong Hoi, for example, receives the majority of its rainfall in September, October, and November. And so when these winds reverse during the autumn and are now coming from the northeast or the east, this brings moisture to Phong Nha-Ke and the surrounding region. And so by studying both climate on the western side of the Trungsung Mountains, as well as the eastern side, we can generate climate records for both of these locations and look at the different seasonality of monsoon precipitation across Southeast Asia. And that is because the Trungsung Mountains actually are the dividing line between these areas that are getting more autumn rainfall versus more summer rainfall, because of the barrier that they pose to moisture transport in the region. Okay, so the study site that I'm going to talk about today is a cave located in Phong Nha-Ke called Hua Hung Cave. And you can see a picture of myself, as well as my student Elizabeth Patterson and my postdoc Annabelle Wolf, located here. And then here's a picture from inside the cave looking out at the entrance, which is a large sinkhole here. So this cave is an undeveloped cave that is very beautiful and actually extremely well suited for the work that we're trying to do. We have first visited this cave actually in March 2020, just before the COVID lockdown, and we began monitoring different environmental parameters in the cave, including the temperature, the humidity, the CO2, the drip rate, water chemistry, etc. And we've returned to this cave twice since March 2020. The first time this back after COVID was just last summer in August 2022. And then we were there again in March 2023 this year, during which we are very excited that we were able to sign a memorandum of understanding between the University of California School of Physical Sciences, where I work, and the Phong Nha-Ke Management Board. So here's just a photo from that. So in Nha-Ke Cave, which I'll refer to as HH, we collected initially one very long stalagmite sample that was about 4 meters long. If you see this, you can see that there's actually multiple pieces of this stalagmite, and here's just one of those pieces. And this, or actually a few of those pieces, I think, fit together. But in any case, this stalagmite was in pieces previously broken on the ground, and we've committed to only collecting broken stalagmites from within the park, so as not to damage the aesthetics of any of the caves in this region. So this stalagmite in particular, we have dated by uranium thorium dates, which shows that it formed between about 4,000 years ago and 45,000 years ago. And this change in slope here is showing how it grew relatively fast during the current warm climate of the Holocene, interglacial, but during the last glacial period and the deglaciation, it grew quite a bit more slowly. We've recently published, actually just this week, the paper came out in the Proceedings of the National Academy of Science journal, led by my student Elizabeth Patterson, as well as with many co-authors from Phong Nha-Ke from VNU, and from other universities. And so I encourage you to look this up if you want to learn more details about the work that I'm going to present today. I also wanted to briefly mention that we are working in another cave very nearby to HH, which is Tham Nung Mai Cave in Laos. And this cave is part of the larger Sibang Phai cave system. It's actually located only about 50 kilometers away from Nha-Ke Cave. And we have been monitoring this cave since 2019, when we visited it and collected samples in collaboration with GIZ. The proxies that we are measuring in this cave are expected to record summer monsoon rainfall, whereas HH Cave, we believe, is more sensitive to autumn rainfall. So by getting 2 records of climate change from both of these locations, we can learn more about what influences both the summer and the autumn monsoon systems in the region. And we have less work completed on this cave. This is showing one of the samples, which is this beautiful stalagmite that spans the last about 16,000 years. And this is just showing some of what some of our cave monitoring equipment looks like. This is a drip logger here. And this is actually just a glass plate that we place under the drip to grow calcite, so that we know what the chemistry of modern calcite forming in the cave is. Here we have the data from HH1 now. This is showing a number of different geochemical proxies. So we have, oh, sorry, my marker's going a bit wild here. Okay, so we have the top is showing growth rate, showing that change in growth rate that I mentioned. This is going from 0 back to 45,000 years on the x-axis. This uranium proxy, the magnesium calcium proxy, and the carbon isotope proxy, and the oxygen isotope proxy all share a lot of similarities, even though they're controlled by kind of different processes. I won't go into the details about the controls on these different proxies, but just know that the direction of the arrow towards the top is highlighting regions that time periods that are wetter, whereas areas for the bottom are drier. And so we see that we have dry conditions during these periods located with the yellow bars. These are actually abrupt millennial scale climate events called Heinrich events, or the Younger Dryas. These are periods when you had rapid flooding of icebergs, rapid release of icebergs into the North Atlantic Ocean, which caused ocean circulation to change in such a way that it affected climate globally, including a significant drying in other parts of the Asian monsoon region. So this is this meltwater forcing that I'm going to refer to later. You can also see, though, that in general, during the glacial period, we had drier conditions. The last glacial maximum was here at around 21,000 years ago. And you can see that in general, that was a relatively dry period, even beyond the range of these Heinrich events. So if we want to compare this record from Vietnam to other records, we're just going to look at the carbon isotopes here because they look quite similar to all the other proxies as well. You can see that, first of all, if we want to compare it with the Greenland ice core record, which is up here, this is a record of climate from Greenland. We actually don't see a lot of similarities. We see a little bit during the Holocene, the last 10,000 years, relatively similarly stable. We see some of these abrupt millennial events, which are these like wiggles that you see here, for example. We also wanted to look at the relationship with the Chinese Lus records of the winter monsoon strength, which here's one picture here, one figure here from a paper by Sun et al. And this is showing, for example, that the glacial period was generally dustier, drier, stronger monsoon than the interglacial period. The Chinese stalagmite record is also shown here, and this is China has a much longer stalagmite record. The reason why we're focusing on Southeast Asia right now is because there's very few paleoclimate records, whereas in China we now have a 640,000 year long continuous record of East Asian monsoon intensity. And we do see some similarities, but also quite a few differences between the Vietnam record and the Chinese record. And then we also wanted to point out the sea level curve down at the bottom, which is showing the changes in sea level that were driven by growth and then melting of the polar ice sheets during the last glacial period or the last ice age. And we noticed that there are some similarities in the broad trend between Vietnam rainfall and sea level. And that's going to be the reason why we focused on some of these additional things. So just to summarize, we find very little coherence between the winter and summer monsoon records, but we do see some links with Greenland and with the global sea level curve. And then if we look at that in a little bit more detail, we actually see that this really abrupt rise at the end of the deglaciation, or towards the end of the deglaciation, corresponds with a very rapid increase in sea level. So this is something that we wanted to pursue a little further. And to do that, we used a climate model called iTrace. This is actually a transient climate model simulation. So it simulated climate through time continuously between 20 and 11,000 years ago, using an isotope-enabled version of the Community Earth System model, ICESM. And the great thing about this model is that there were several different runs that combined different factors. And so you can look at the isolated impact of things like the size of the ice sheets and sea level, the concentration of greenhouse gases, the degree of meltwater forcing through these iceberg calving events during Heinrich events, and so on. Okay, and here we have a picture of, again, our proxy data on the top. The middle panel is showing the precipitation data as simulated by iTrace, showing that it generally is suggesting that conditions were relatively dry during the glacial and then increase quite a bit around 14,000 years ago, again, in line with our proxies. We also see a shift in the delta 18, which occurs a little earlier, and that's because the delta 18 signal is a combination of just summer and winter rainfall, and actually is not necessarily a great proxy for local rainfall. On the right hand, what you're looking at, this is just showing we're looking at the difference between that sort of wet event that started around 14,000 years ago and the dry event just before it. And we're looking to see if we can identify the seasonal patterns. And the left panel is showing the June, July, August, or JJA difference between those two events, whereas the right panel is showing the September, October, November difference. And you can see that during the autumn, there are anomalously dry conditions over central Vietnam, as well as the South China Sea region where the moisture is sourced from. So what causes this drying pattern is one question we wanted to understand, because this impacts our ability to understand future rainfall change as well in the region. And so this drying pattern, we can use the model to understand what was happening during this time. And we've already noted two major potential forcings, both meltwater into the North Atlantic, which affects ocean circulation, as well as sea level. And so if we look at the combined forcing, this is the same picture I showed you before, where we have this broad drying over the South China Sea, including regions of Eastern and Central Vietnam. If we want to isolate the impact of just meltwater forcing on autumn precipitation, you can see that meltwater forcing causes broad drying across kind of much of the region. And this is related to a southward shift of the intertropical convergence zone and changes in circulation in this area, as well as sea surface temperatures. Down below, if we want to just isolate the impact of sea level, we see that sea level actually has a very focused impact in the South China Sea regions, where the autumn precipitation is sourced from. So to show a map version of what sea level impacts would have done to the region, this is showing a very recent sea level construction, looking at where the coastlines or shorelines would have been at different times in the past. So during the last glacial maximum, or LGM, the shoreline actually along the South China Shelf here and the Gulf of Tonkin was much more distal from where it is today. So all of this area here would have been dry land during the last glacial maximum. And you can see this is directly upstream or from the cave sites. At 14,000 years ago, there was a sudden sea level rise that flooded much of this area, bringing additional moisture that could be sourced from the region. So if we want to look at the combined effect of sea level and meltwater forcing, this is showing atmospheric circulation patterns, vertical transport, with the red areas showing areas where you had decreased convection during the last glacial maximum when we had lower sea level. So less convection. We also had cooler temperatures, surface temperatures in this area during the last glacial maximum. So both of those factors would have contributed to lower moisture delivery to central Vietnam. So this is showing that Vietnam rainfall patterns are very subject to large and abrupt changes. And we are moving forward with additional studies to understand what causes rainfall variability on shorter timescales as well. And hopefully we'll eventually be able to identify and look at previous warm periods to understand more about what we can expect in the future for Vietnam rainfall. But just to conclude, we presented a 45,000-year record of the Southeast Asian autumn monsoon. We've identified two primary controls of rainfall in the region on these longer timescales, centennial to millennial, and that includes meltwater forcing in the North Atlantic. So melting of the ice sheets, for example, today has the potential to impact ocean circulation, and that, based on this, would lead to potentially drier conditions in the region. Sea level lowering is not likely to happen at the present, but one thing that this work really showed us is that the model is capturing the impacts of sea level very well, and therefore we can have more confidence in some of the climate model projections from ICESM. And then finally, I just wanted to briefly mention the fact that we're hoping to organize a workshop in Phong Nha in the summer of 2024, so next summer. And this will be a 3-day workshop focused on past, present, and future climate change impacts. We are just starting to think about organizing the logistics, and we will be working with the Phong Nha management on this. But we will have funding to support travel for participants from Southeast Asian countries, and we're seeking additional funding to make this workshop as accessible as possible for everyone. So if you're interested in that, you can shoot me an email and we'll make sure to add you to the list for when we are announcing the event. And then for just briefly as well about future directions and opportunities, we're very excited to continue studying paleoclimate so that we can improve climate model projections in this area. But we also have collaborators who are working on aspects of paleoecology, on archaeology, looking at human environment interactions and resilience to past climate changes. We are looking forward to learning more about the difference in climate between the Western summer monsoon dominated regions and central Vietnam. So by comparing our work from Hinh No and Phong Nha-Ke, we're hoping to help encourage researchers to come here to collaborate with local scientists on a range of issues related to sustainability and climate and public health even. And hopefully we'll be participating in some research exchanges where we can actually bring folks to our universities or send our university students and researchers to the park for longer periods of time in the future. So with that, thank you so much for listening, and please feel free to email any questions to me that you may have, since I won't be there to answer them in person. Thank you so much, and I hope you enjoy the rest of the conference and look forward to hopefully hearing more about all of the research that's happening in the park at another time. Thank you.